Hello, I'm Mathieu Larouche, Product Manager at Matrix Imaging. Today, I'm here to present how using multiple 3D profile sensors can enhance the fidelity of a 3D scan. Before we start, you may wonder why you would need 3D vision. Some inspections require taking into account the third dimension. For example, the volume of an object, the height or tilt of a feature, and the flatness of a surface. Another use of 3D could be for aligning an object that is not resting on a flat surface, or guiding a robot to pick randomly stacked parts. Finally, you could use 3D imaging to improve standard 2D analysis if you cannot obtain the necessary contrast. In this case, 3D imaging is used as an alternative illumination technique. 3D profiling is a long-standing and well-established technique for generating a three-dimensional representation of an object. It uses the principle of laser triangulation, whereby an image sensor views a laser line that projects onto an object. The laser line bends to follow the contour of the object, which results in a profile. Object length is determined by accumulating profiles at regular intervals by either moving the device or the object. 3D profiling in general provides excellent resolution for useful field of view when compared to other 3D scanning technologies. The Matrix LT is a 3D sensor that provides a 3D representation of an object or a scene. The higher fidelity comes from the dual camera design, which minimizes optical occlusions. The algorithms are implemented in a processing pipeline running inside the LTs and generate a depth map or point cloud, which minimize the involvement of the CPU in acquisition. To interface with the PC, the LTs uses a GigaVision interface, which makes it fully compatible with software, either ours or third-party, that supports this interface. The optical occlusion phenomenon is not to be confused with the laser fan angle effect that will be covered later on. The optical occlusion is caused by the laser line being obstructed from the view of an image sensor because of surface orientation. The opposed sensor design of the LTs is able to mitigate the effect of this kind of occlusion. Here is a slide presenting the differences between scanning with a sensor, which has only one camera, and one using two cameras. The left one was obtained using a single camera. The middle one, the yellow point cloud, was obtained using the two opposed cameras. To better see the difference, the right one is the result from merging the right and the middle ones. The solid yellow areas in the merged view show where the two opposed cameras are able to detect a surface where a single camera cannot. Okay, this presentation, we will see how using multiple 3D laser profilers can improve the resulting scan. There are several reasons why you may need multiple sensors. Let's take a closer look at some of them. The first one, which is kind of obvious, is to increase the scanning field of view. Installing two laser profilers side by side allows you to scan larger objects while keeping a better resolution. This is useful for large surface inspection since the features that you are looking to detect are typically small, which will require a good resolution. So using multiple 3D profilers together extends the field of view, but has also the benefit of mitigating the occlusion due to the fan angle of the laser, which is a limitation of a laser profiler. This occlusion is caused from the fact that the laser doesn't hit the bottom plane directly besides the object. This effect is worst on the edge of the field of view since the angle of the laser light is higher compared to the middle of the field of view, where the laser is almost perpendicular to the plane. Using a second 3D profiler to overlap on the edge of the field of view will mitigate this effect. The area that is not seen by one sensor will be seen by the other, and so on. The two previous examples were showing applications where the sensors were installed on the same plane. If you incline the 3D sensors, it allows you to scan areas of the object that wouldn't be visible otherwise. This could be very useful in scanning objects with vertical edges or to calculate volume of irregular objects. This is widely used in food inspection applications. Now that we have covered the possible benefits of using multiple profiler, we need to understand how this can be done. One challenge when working with multiple point clouds is to find the geometric transform between each in order to merge all the points within a unique point cloud. In other words, you have to make sure that all the point clouds are based on the same reference point before merging them. Depending on your configuration, the operations to be applied could either be rotation, translation, or both. With MILX SP5, we provide an utility that will help you find the relation between 2 point clouds. You have to scan an object beforehand and walk through the step of the utility to obtain a geometry file that can be used after in your application. This ensures that the merge of the point cloud can be easily done in your application at runtime. In the following slides, we will see some examples where using 2 profilers bring great benefit. To demonstrate the benefits, we built a setup to show some examples. 2 matrix Altice laser profilers are used for the acquisition and are installed slightly inclined towards each other. They are connected to a Matrox Foresight XV6 industrial PC using a Matrox Concord PoE network adapter. A Matrox I/O breakout box is used for the Altice synchronization. The industrial PC is running a MILX-based application. A video explaining this demo in details can be found on our website. But let's take a look at the resulting point clouds. The first example is food inspection. In this slide, the red point cloud is a scan from the top using a single Altice. The blue and red point cloud on the right-hand side is a merge of the 2 Altice scan. As you can see, using 2 matrix Altice will provide more points on the object. It is especially true for the sides of the spheres, which are not visible using a single Altice scanning from the top. We could even have more points by increasing the angle between the 2 sensors. Then the processing operation will give better result if there's more information in the object. In this case, it may not be clear on the picture to the left, but the clementines on the outside are a bit smaller and the radius calculated using the 2 Altice setup are closer to the real radius. The second example is the mounted stud inspection. The images on the right are 2 distinct scans using a single Altice. The first one, the red one, is a scanning from the top, and as you can see, only the top of the studs are visible. This is clearly not good enough for this application. The second one, which is in blue, also comes from a single Altice, but the scan was done with a sensor slightly inclined. While it provides more information than the scan from the top, we only see one side of the cylinder, so information is still missing. In comparison, merging point clouds from 2 matrix Altice scans will provide a lot more information on the scene. As you can see, all sides of the studs are fully visible in this 3D representation. Also, we can see that there is no gap left on the bottom plane. That allows us to do a better cylinder fit and get more accurate measurements for the stud radius and for the angle between the stud and the bottom plane. The final example is locating electrical plugs. In this slide, you can see the electrical plug scan using a single Altice on the top left. On the top right, we have the exact same plug, but scanned using the 2 Altice configuration. We can clearly see that the plug on the right has a lot more information than the one on the left. It is especially true on vertical faces of the plug that an Altice scanning from the top cannot see. Since some features are missing from the scan using the single Altice, the blood analysis tool and the volume tool don't give accurate results. The results are a lot better using the merged point clouds from the two LTs. There's many other applications that may benefit from using multiple 3D sensors. It really depends on what is the problem you're trying to solve. The Matrix LTs is offered in 4 models covering 3 measurement ranges to address many different applications. Many factors will dictate which model is needed for your application, but typically it will depend on the size of the objects and features, the scanning height, and the resolution needed. The surface of the object may have an impact as well. Alongside our hardware offering, we do offer software. The Matrix Imaging Library contains a rich set of tools for processing and analysis. It allows you to develop powerful applications for machine vision. The offering in 3D is always expanding and is able to help you solve challenging problems. Matrix Design Assistant is a powerful flowchart-based IDE for developing machine vision applications. It is based on our Matrix Imaging Library and supports many 3D sensors, including the Matrix LT's 3D Profiler. This software allows you to greatly shorten the development time for your machine vision application. CaptureWorks is an interactive tool to configure and set up the Matrix LTs, but also 2D and 3D cameras that are based on GenICam interface like GigaVision, USB 3 Vision, Coax Express, and GenTL. This utility is easy to use and allows manipulation of point clouds or 2D images. Matrix CaptureWorks come with both Mill and Design Assistant. Thank you very much for listening. And if you need more information on the Matrix LTs or the other products mentioned in this presentation, please visit our website at matrix.com/imaging.